Hello, I'm Larry Hoffer, AIS's Executive Director, and I'm very pleased to welcome you to our webinar today. We are very excited to have built a new partnership with the American Institute of Steel Construction, AISC, and we'll be working with them throughout the coming year on a number of different programs. This is our first webinar together, and I would like to turn it over to Jean Homer with AISC to get things started.
Thank you. And we are so happy to hold our first Thrive webinar with AIAS. I wanted to tell you a little bit about the American Institute of Steel Construction. We're more than that thick manual that some of you may own. We are a nonpartisan, non-for-profit technical institute and trade association for just over 100 years. And we serve the structural steel design community and the construction industry in the United States. We do a lot of behind the scenes research and education, things to look forward to what are the new developments, and also to keep things safe. So behind the scenes, we're also looking at updating codes and verifying professional certifications. And we like to form close working relationships with architects and engineers and construction professionals. I'll do a brief introduction of myself. I'm an architect and I taught architecture for over 22 years, 20 years of which were at Oklahoma State University, go Pokes. And I had to move home to Chicago, but I'm happy to still be interacting with students through AISC. And speaking of students, we do a lot with students. You may be familiar with the ACSA Steel Design Student Competition that has been held since 2000, so a pretty long run. You're seeing some of the first place prizes from last year. On the left are the category 1 of the monument, and on the right is the open category. So you design anything as long as it's with steel. This year, the program is a spiritual space on a campus of your choice. You can do this alone or as part of a studio, but you just need a faculty sponsor. So you can read through that program on the website, and we still have the open category just as we always have too. We give lots of scholarships out. Last year, we had over $360,000 given away to juniors, seniors, and master's level students. And so we hope we have a good showing for these scholarships. One side tip is that we have a small essay, a short essay, and you need to focus on steel for that. We have free membership for students, so you get some perks. You're going to get this amazing magazine every month, and the perks continue a bit after you graduate. And of course, we formed this amazing partnership with AIS we're very excited about, and we're able to offer you, even through this course here, health, safety, and welfare credits that I understand you can use toward licensure. We also facilitate a lot of hands-on opportunities, maybe in studio, but also at Grassroots next summer, we're holding a tour at the Ironworkers Training Facility just outside of DC, and you can weld, bolt, climb columns, a lot of different things there to get some hands-on experience. We encourage other kind of steel activities like touring a fabrication shop or going on construction tours. If you can't do that physically, we have VR tours that you can walk through on our website. And I mentioned emphasizing career-long partnerships. We have a Steel Solutions Center that architects and engineers can call into for anywhere from conceptual ideas and solutions to something more detailed. And you're going to hear more about this today, but if you're designing with sustainability in mind, structural steel is actually a really good choice. U.S. domestic steel is truly cradle to cradle. That loop is closed. And every time it's recycled, it doesn't lose quality. So domestic steel is made up of 93 to 98% recycled steel. So we'll take old cars, appliances, deconstructed bridges and buildings, and we'll keep those out of landfills, and that scrap is melted into new steel using electricity. But a steel frame building in the first place is less likely to be scrapped. Steel buildings over their life have lots of flexibility. If occupancy or loading changes, it can be more readily adjusted, and you can have longer spans so the interiors are much more flexible. We have lots of transparency in terms of reporting about embodied carbon of the life of steel material. So we have extensive environmental product declarations that anyone can view. So in the US and Europe, electric arc furnaces are used, and they're a much cleaner technology than blast oxygen furnaces. But so now the focus is shift toward the electricity to power those, and a lot of mills and fabrication shops are moving toward renewable electricity. And you'll hear more about that, but we mentioned you can get health, safety, and welfare credit. I wouldn't write all this down. I would just focus here at the top. We have a website, aisc.org/AIAS, just for you, and we'll have all the information on it. But we won't have the quiz code on it. You just get that here in the video, and that's AIAS 816. So there is a couple steps to get this credit. So you'll form an account, and then you'll go through these directions here. And from there, you'll be able to access a quiz and then get a certificate after you complete the quiz. If you don't get 80% the first time, you can retake it. It's just a requirement of AIA courses. And here's just some screenshots. So that's once you're in the course, you could click quiz, and when it says quiz password, that's where you plug in the AIAS 816 code. If you have any questions or ideas, I would love to hear from you. At my email is homer@aisc.org. And with that, I'm going to turn it over to our presenter, John Hand.
Thank you, Jean. I'm going to switch to my screen. Excellent. Well, hi, everybody. Thank you, Jean. I'm very excited to be joining this webinar and talking today about architecture and hybrid structures, maximizing the benefits of structural steel and wood floors. So what does that mean? Well, we'll walk into that. A little bit about me. I am a structural engineer by training. I'm an associate at Arup, a global engineering firm based in the Houston office. I actually have an architecture background myself. I started undergrad in architecture school and finished my undergrad in architecture. So I'm sweating with you guys and thinking of you going through all your sort of final presentations and understand where you're at. So I'll be talking about some structural items. We've tried to make this a little bit geared towards students. So we'll talk a little bit more about that, but hopefully you enjoy this webinar. This is a presentation that's geared around the new design guide, 37 hybrid wood or hybrid steel frames with wood floors that Arup worked with AISC on publishing. You can actually go to the website and design this full document. So anything that we're talking about here today, you can actually get in a lot more depth ultimately through this design guide. This was co-authored with a multidisciplinary team across Arup, so several structural engineers there, but also acousticians and fire engineers, sustainability consultants as well, to try to create a holistic guide that could be approachable by a broad audience. So the main focus and audience was certainly some structural focus. There are some sections that were geared towards structural engineers, but really we tried to be broader as we crafted this to talk about the typology of hybrid steel frames and wood structures that could be accessed both by architects as well as owners and developers who might want to know a little bit more about why you would entertain this system, what the benefits might be, and how it might be applicable to their project. Now, what do we mean? Hybrid steel frames with wood floors. So I figure we'll just start with this image. This is a picture of Houston Endowment headquarters in Houston. It's about a 2-level office structure. And what the red arrows are pointing at are 2 things. First is the steel framing. That's the kind of the red, dark red, maroon kind of primed steel. That is the columns and the beams. That is the main skeleton and frame of this structure. And when we say hybrid wood floors, what we're talking about is that timber that's then spanning across as the floor plate. And why is this different? Why did we write a whole design guide about this? Well, traditional construction with steel buildings, especially commercial projects, a lot of the times we've used concrete as that framing with metal deck, and it's a very effective system. The reason a lot of buildings use it is it's a good system to use. It has some benefits, and essentially that metal deck that you see from the underside looks a lot similar to that previous issue. And that metal deck has studs to connect the steel to the concrete. There's some reinforcement, and that steel deck acts as formwork from which then to pour the concrete on top. And the concrete actually works together with the steel to be a composite structure. And that's what we call this type of system, a composite concrete steel on metal deck with steel structure. And this is looking at it from the top. Again, you can kind of see these are called studs. They look like little screws that are welded and connect the metal deck to the steel, and ultimately then the concrete's cast over to have it act together. And really, again, going back to this image, what we're doing is really taking that concrete and that steel on a metal deck and replacing it with mass timber products. And that's really what we mean by hybrid steel with wood floors, and what this design guide is focused on. There's other typologies and other ways to use hybrid structures, but for this one, this is really the lens and the focus that we're going to go through. And we'll talk about why this is a little bit new and why we're seeing it more and more in the marketplace, and where owners, developers, architects are asking for this. And the way we're going to chat through it is really just going through the chapters. There are 7 chapters in total that we're going to walk through, and we'll kind of go through the highlights on a lot of those. And really, we're going to end with pictures, something that you can kind of see an actual building, how it's put together, to try to understand those components. And that is going to be our case study with Houston Endowment at the very end. So let's just dive straight into chapter 1 and really go into mass timber background information in kind of the first chapter. So first thing, what is mass timber? Well, we'll start with the opposite as well. What isn't mass timber? It's first off, it's not stick framing or balloon framing. You might see in especially kind of the suburbs, a lot of homes that are maybe built like this out of really small 2x4 material or plywood. That is not mass timber. We usually refer to that as stick framing. Likewise, what's mass timber is not heavy timber. And what heavy timber is sort of the opposite of the 2x4s. You actually get a tree and you say, all right, well, let's go for a big piece of lumber. That's got to be mass, right? It's like, well, no, that's heavy timber. That's where you now have a larger piece of timber that's cut out of essentially a historic tree. And this is the way warehouses were built. As you see on the right-hand side, a lot of industrial buildings in the 1800s were built with masonry walls, and then they actually used heavy timber. You can see those beams that would form the columns in framing. And that's really a heavy timber typology. Here's kind of another image. And that's actually defined in the code by heavy timber of having a large enough size. And what happened is some of these buildings actually burned down and they had a fire, but they did not collapse. And they actually have known for a while and have built this into the code that heavy timber that's large enough can actually char and protect itself, and you can actually get a fire rating of it. And if you go into the IBC, into the code, that's how heavy timber is defined. It's defined about its fire rating performance and having a big enough a piece of wood to where under fire conditions, it's essentially not going to collapse. So there actually is a definition for heavy timber, but really when we say mass timber, it's kind of the next generation version of that. So heavy timber on the left-hand side, cut down a really large historic tree. You can't really find those anymore if you want to go have a very long span or have a big element. And so what we do is we've actually have more new growth trees and smaller members that we can then kind of cut into components. We can then actually look at the pieces of timber and rate them, and we can see which ones are really good and high performing, which ones are maybe not as good. And we can optimize how we put those smaller pieces of timber together with some high performing glues, and then we can create large timber elements out of these smaller elements. And that is fundamentally what mass timber is. You're creating an engineered product out of smaller pieces of timber to make a bigger element. So pretty similar to heavy timber at the end, but how you build it and how you engineer it is much different. And some of the benefits are you can get a much more stable product because you can really scan and look at each small piece of timber. You can rate it. You can get some very high performance products. You can also get almost a size of any type of element that you want. And really what's changed in the last decade and plus is now you can get panelized mass timber products, not just glulam beams and columns, but actual plates and materials that can be used as pieces of floor plate. So again, this is, for a full mass timber building, a lot of times all the elements are created out of mass timber elements. That's not really, again, our design is more of a hybrid, but really the mass timber floor could be any one of these elements. And mass timber is a big category to capture a lot of products. So for example, glulam beams are linear elements, but you can actually turn them on their side as planks and use them as a floor plate in a steel frame structure as well. But really what we're geared towards and what this design guide is geared towards is the most kind of one of the more prevalent materials is cross-laminated timber, or I'm going to refer to it as CLT pretty much for the rest of our talk here. And CLT is generally 8 to 12 feet wide panels that are somewhere around 40 feet long that can fit on a truck that you can use as floor plates or then as wall elements. And you can make them almost as thick as you want, from 3 plies, kind of 3 levels of lamination, to 9 plies plus. You can get some very thick, large pieces of panels. And they're very high performing. They can have some long spans, and it takes away the need to add metal deck and that manual labor aspect of welding, adding in the rebar, pouring concrete. You can now replace that with a more prefabricated element, similar to a hollow core plank is another, for those who have used or looked at precast panels. Sometimes that's used with steel framing as well, where they drop in precast panels. So kind of a similar typology there. We're just going to go through these others just to show their names. There's timber concrete composite panels. There's nail laminated timber, where you nail 2x4s, 2x6s, 2x8s together to create a panel, and you can even do these on site. There's dowel laminated timber, which is a proprietary product, which is similar to nail laminated timber, but you actually use dowels to connect it together. So there's no nails at all. It's a pure timber product. There's laminated veneer lumber. Then there's laminated strands lumber made out of really small kind of plies that you carve off the tree trunk. And there's even true mass plywood panels. They're literally really large pieces of plywood. And there's new products really being developed all the time for different conditions. And all of these can be used, again, really with this design guide. But for our purposes, we had to focus in on something and are really focusing on the CLT. Again, just from a ply definition, what you're seeing here are 5 plies. You can count up each layer is a ply, and this is showing 5 of them. The typical plies that you would normally use would be 3 ply. It's somewhere around 4.5 inches thick and goes about 10 feet generally for common loading in an office or a residence. 5 ply is typically around 15 feet and is closer to 6.5 inches. And sometimes for 7 ply, if you want to go 20 feet and have a much longer span, you're going thicker than that, and you're adding 2 extra plies to that. So that's really what we mean by ply when we talk about it for here on out. So kind of introducing those systems, what is the advantage? Why would you consider this for a product? There's a lot of options out there. Well, First off, a lot of times from an architectural standpoint, especially in your classes, aesthetics might be a driver in biophilia. If you're wanting to have a warmer space and you want to have timber, instead of having a timber drop ceiling, you could actually express it and use it as your floor plate. And it gives you a way to express your structure and use that as your ceiling and take away having to add a drop ceiling. And aesthetics is certainly one of the big drivers that we've seen from clients and from architects wanting to use it. It's a beautiful look. Wood is beautiful, and wood together with steel has a beautiful look as well. This is the interior of Houston Endowment rendering. Sustainability is another driver, as Gene sort of mentioned in that sustainability is a big driver on our structures, and structural engineers are being driven with architecture to pull out carbon from our buildings as much as possible. And some developments even require you to track it and present it. And a big portion of the carbon in our buildings is in concrete. And if we go back to steel buildings with concrete, again, sometimes it's a good use, but if you're looking to take out carbon and you can pull out that concrete, the timber we'll talk about later on has a much smaller carbon footprint than concrete, and you get a lot of savings there. So that's a big driver too. Likewise, you can have longer spans with a mass timber floor building sometimes, just due to the fact that it's actually lighter. It can be lighter than a concrete and composite metal deck. And also compared to a full mass timber building, you can sometimes run into trouble for beam depths if you're trying to go a long span. And this, for going something a little bit longer and wanting mass timber, steel offers a lot of flexibility and advantages for having a much smaller floor-to-floor height. Likewise, the columns in steel it's a very high-performing material. We can get our columns a lot smaller than a mass timber building generally would have. And you also can have a lot of flexibility with how you attach to the facade. Steel does a really good job with shelf angles and all those attachments that you need with cladding that other typologies would sometimes have difficulty with. Likewise, with steel, we can generally get penetrations and kind of coordinate our MEP routing or MEP services, have a lot of flexibility in how we go through those spaces. And that's another reason where steel, having the steel beams and steel framing as opposed to sometimes glulam beams, you can get a thinner profile overall. And a big one on the cost side, so from a developer side and a contractor side, obviously schedule and cost is a big driver. And that there can be some advantages there as well due to the fact that it's a prefabricated panel. As you can see here, those CLT panels are being brought to site off a truck and dropped straight in. They're lightweight, and because they're lightweight, you don't need as heavy equipment. So you can actually have a smaller site, a cleaner site. You can have a smaller crew. It's safer with fewer people and lighter equipment, and the building can go up faster compared to other typologies and laying on metal deck and concrete. So that's a real big driver on the developer and contractor side. And again, the site logistics, especially for urban sites or tight sites, because of that prefabrication tied to it, sort of a similar advantage there. So what does it look like practically if you were to draw this out, just to give you a sense of a framing plan? So this is a floor plate for what might be a typical office building. And you can see the columns are wide flanges. Those are the I-beams you might notice, you might call them. That's for an office building might be 30 feet wide in a bay by 40 or 45 feet. That's fairly common. This is showing 5-ply panels that are going left to right between the secondary beams. And you can see the secondary beams that are going kind of north-south on the page are around 27 inches. And then the girders that are going left to right that are picking up those beams and going to the columns also at 27 inches. And this is a fairly kind of a typical plan in order of magnitude sense of how this is laid out. And we'll talk about it later on, but part of the optimization that we look at and making it efficient is having a good grid size, a good base spacing that helps limit waste in the panels so they can cut them, bring them to site. And it also is efficient from a steelwork framing standpoint. But this is a fairly fairly common commercial office bay that you might find. Also, how you deal with the sandwich of the floor plate from an architectural standpoint is a real big deal. Really, a lot goes into that sandwich. It's not just a piece of timber that's doing a lot of things for you architecturally. It's your floor finish. It's also working for you acoustically. It's your ceiling. It does a lot of things, and how you consider your sandwich is something that you really have to coordinate with all your consultants. And it's something as you're designing in your studios, you want to think about the acoustics. You want to think about the aesthetics. You want to think about how are you routing your mechanical systems. And really, there's kind of two main kind of floor sandwiches that you end up with. On the right-hand side, you can see there's a CLT framing that's on top of a beam, and it's screwed in from underneath. But on top of that, there's additional buildup of an acoustic mat with a mass topping on top, in this case, 2 inches of gypcrete. And we'll talk about that in the acoustic section, but that's a fairly common sandwich. On the left-hand side, what you can also do is then have a raised access floor, and that's really the difference on that left-hand side. And that raised access floor allows you to put in your mechanical ducts, your electrical routing on the top side as opposed to the underside, and hide a lot of it, and also provide an additional sandwich there. So those are kind of two kind of floor plate typologies that we'll generally see with these buildings. And again, the multidisciplinary aspect of this is really what makes this fun. It is new, relatively new, and it forces consultants and designers to talk and figure out these issues. As you try to tweak the acoustic issue and how you deal with acoustic, you might be adding more mass, which impacts your structure, and that structure might impact your sandwich and your overall height and your facades, and how it looks and feels aesthetically, and how the spaces feel. So you really have to think through all these issues with this type of methodology, and there's more and more precedents and buildings coming out, and it's really exciting to learn. So definitely a lot out there. So let's step into a few of those issues that we kind of talked about here just really quickly. Fire design is a big one. As you as an architect, you will be responsible for generally the life safety of this building and saying whether it meets code from a life safety standpoint. Sometimes there's a separate consultant. There are life safety consultants, but a lot of times you will be working with them, or you'll have your own team where you say, what type of building is this? What's the fire rating? Do I need sprinklers or do I not need sprinklers? All of that is part of that analysis. And structurally, for different size buildings, as you get bigger and bigger, there is a fire rating that you're required to have on your structure. And kind of a myth, again, going back to it, is that if you have timber, timber it's just going to light on fire. It's a big fire risk. It can't stand up. And that's not true. Timber, yes, it can ignite. It's combustible, but there's good testing and documentation as far as understanding if it's thick enough, if it's heavier enough that it can self-char and form, that char can help provide a resistance for 1 hour, 2 hour, 3 hours in order to, under a fire condition. So this is a picture of, you can see it during a fire test where that charring is happening, and that bottom layer is in really bad shape, but that upper portion is still fine. And we actually can design our, for example, CLT floors. There's calculations we can have to determine how much under different hour fire, how much we would lose. And so we can calculate if we need to make it thicker on top in order to deal under a fire condition, still be safe for firefighters or people to leave the building. So that fire rating is essentially, if you have to rate your structure, you have to get a little bit more timber into your product in order to provide that charring. So you're basically buying sacrificial timber as your fireproofing strategy. Additionally, you could cover it. If you're required to fire rate it, you could cover it. You could put gyp board on it, for example, or other strategies to provide a barrier between the fire and the combustible material. And sometimes, as you'll see in the code, it does require you to encapsulate that timber. On the steel side, if you've probably seen fireproofing on steel where it's been spray applied. So for steel, generally you're still either applying that, but if you're exposing the steel and you want to see the steel and you don't want to see that cementitious or kind of fiber fireproofing, you might paint it with what's called intumescent paint. And that intumescent paint under fire conditions expands, and it kind of looks a lot like that char image. It forms a big insulating layer under fire when heat hits it and actually protects that steel. So you would still use those if you have to fire rate your steel, and that wouldn't change. As far as how tall can you build with steel and mass timber, well, the code actually in 2021, the International Building Code has provided some good clarification on having mass timber in buildings as part of your structure and how tall you can go. And as you can see on the right-hand side, there's now 3 types of building. There's a type 4A, type 4B, type 4C. And what you're going to see is on a type 4C, you can go up to 85 feet effectively, 9 stories of office, let's say, and you can completely expose all of that CLT floor plate. And that steel can be exposed as well. The steel has to still be fireproof. The CLT has to be rated for a fire condition, but everything can be exposed. On the opposite side of that, if you want to go to 18 stories all the way on the A, the code actually dictates that you have to encapsulate all the exposed timber. So even though you can design for a fire rating, as you get really, really tall, the code is saying, well, now, that's great that you have mass timber in there, but you can't actually expose it. You can use it for structure, but you can't expose it. And then the type 4B is basically an in-between, where a certain amount of the mass timber can be exposed, but not all. And when we mean partially exposed, we mean something like this, where you can see on the right-hand side above the kitchen, it's encapsulated with gyp, it's not exposed, but then over the living room or main spaces, you might expose that CLT in those spaces, in those structures. So you can use mass timber, you can use it in the code. With your steel structures, there are limits to how you might have to encapsulate it, but those, hopefully that's a helpful guide for more info. There's lots and lots of info out there. We're just really touching it at a high level here. Just a pointer on the intumescent paint. If you're detailing that for your review, you don't have to paint the top side. The mass timber on top of it will protect that steel and serve as that insulation on the top. So acoustics, at a high level, really what we're dealing with are 2 types of noise on acoustics. The first one is a sound transmission class, and that's how sound kind of transmits or blocks. So think of, I'm in a conference room right now. I could be right next to a next conference room, and if someone has their speaker on, that speaker is going to transmit noise through the wall. And how well it blocks is kind of defined by that STC rating, that sound transmission class. And the better it blocks, the higher the rating. So that's sound transmission. But now on top of me in the ceiling, I could have a really good sound transmission through the floor above me. But if someone walks around, I'm in Texas, if they come around with their boots and start walking on the floor and it's just a hard concrete surface, I'm going to hear that like a hammer, like someone's taking a hammer and impacting it. And that impact is talking about the impact installation class, the ITC. So that impact noise, it doesn't matter how good sound transmission you are, if someone comes with a hammer and starts banging on it, you're going to hear it. And generally it has to do with kind of having spaces above you. And just to put that in an image, again, you can see the magenta ones are sort of the impacts of people walking. That's an issue we got to deal with. And then having enough mass is them talking. That's sort of the blue. That's what this diagram's trying to show. Now, if you were to use CLT in your steel frame building on its own, generally bare CLT is not going to meet either a good sound transmission rating or an impact rating. And the reason it won't is one of the benefits. It's a lightweight material. That is a benefit. That is a great thing. It makes our steel structures lighter. We can span farther. We can take load off the foundation, easier to lift. All those things we talked about as pluses. Well, from an acoustic standpoint, and we'll talk about it with vibration, that can sometimes be an issue because in order to absorb energy, sound is an energy. In order to absorb that energy and stop it from transmitting, you need mass. And so that's one thing where the mass timber on its own doesn't have enough mass generally for these code ratings. And so there's really a couple things we have to do. We have to add mass in some way. A lot of times for the impact noise, we need to add resilience, and or sometimes you can even add an airspace. And the way of most CLT floors, I would say, kind of a general approach to it, is to, again, have our timber structure, and then you have a resilient underlayment. So it's somewhere around, a 1/4 inch to a 1/2 inch of resilient underlayment that they will lay out on the top. It's kind of like a squishy pad. And then on top of that, they're going to pour a mass layer. So call it 2 inches of gypcrete. And that will actually be poured on top. And what happens is that total sandwich of adding that mass together will solve the sound class rating. It'll so that sound doesn't transmit too much. But it also, that resilient layer forms a barrier for heel clicks. So as people are walking across, it goes through that gypcrete layer, but now it hits that resilient underlayment and can't transmit down. So this really solves both of those in a lot of situations. But again, there's a lot of guides out there, a lot of mass timber manufacturers who have sample buildups with different layers of kind of the mass buildup and the insulation. Sometimes they even count on having a ceiling below with airspace, and you can get lots of different ratings. You can nerd out on this stuff, go crazy, but we're not going to cover it in this presentation. But hopefully that's kind of a good intro and give you a sense of why we have those extra layers on top of the CLT and what they're functioning from an acoustic standpoint. Kind of going back into the sustainability side of things, and that Gene really introduced very well. There's a couple of terms there that we just want to talk about, and Gene mentioned kind of the bottom one, the environmental product declaration. So that's really saying how much, essentially from a life cycle, how much kind of carbon is there, what's the environmental impact, and actually having that measured in a scientific and third-party verified way, so that you can also compare products kind of side by side for how they're performing. The two other things we're going to talk about here is just operational carbon versus embodied carbon. So when we say carbon, sometimes people mean one, or they mean the other, or they mean both. So just for our standpoint, we're really talking about embodied carbon as part of our presentation. And what embodied carbon is it really has to do with structures and materials that you bring to your building, is how much energy, how much carbon was put into them in order to grow them, to cut them down, to manufacture them, to bring them to your site, and they're brought to your site, right? And then it's there, and that is the embodied carbon. The operational carbon is sort of the day-to-day continued energy and carbon that your building is using to run, and that's usually things like your lights, your HVAC system. All that stuff has to do with the operation of the building, and that's continual. So that's not what we're talking about here. And when we say net zero buildings, a lot of times people mean net zero, they mean on the operational side. But sometimes you'll hear a term of net zero carbon, where now you're talking about both. So it's really started to come up, especially in Europe. Buildings are measured and evaluated by both the embodied carbon separately from the operational. A lot of times sustainability, especially in the US, has meant really operational carbon. I think the kind of both pictures are coming more and more in balance together. Biogenic carbon is one aspect we're going to talk about in the embodied carbon of sort of how to treat that carbon as it's grown by natural materials, and sort of the carbon as it absorbs the carbon from the sun through photosynthesis, and you have carbon in a tree. How do you treat that as part of the equation? So taking timber, this is showing the life cycle of carbon of a theoretical piece of timber that's used in a building. Essentially on the left-hand side is when it's growing. So you can see it's planted, and over that 30 to 100 years, it's actually taking carbon out of the atmosphere and storing it. It's a carbon negative. It's carbon negative, essentially measured at that point in time. And then after you cut it down, you are adding carbon back in. It's going back up towards negative as you manufacture it, you transport it to site. But essentially, that's that little jump that you see kind of on the right-hand side. And only if you sort of put it in an oven, if you put it in your barbecue pit or your grill and light it on fire, you're then going to release all that carbon back into the atmosphere and back into the environment. But unless you, unless you don't light it on fire, generally it's for the life of our buildings, it's generally still going to be carbon negative measured across that time period. But that's really the question on biogenic carbon, is that left-hand side. And there's, different folks measure that biogenic carbon in different ways and treat it differently as part of the carbon equation. So just be aware of it, and how you're measuring will change depending whether you count that biogenic carbon or not. And it's just something to to be aware of. So as part of this study, and to kind of show the relative benefits of what a mass timber and steel frame building would do, there's a study of really 3 typical floor plates for an office or residential building. A 30-foot by 30-foot normal weight concrete post-tension slab. That's a fairly typical typology for a lot of those buildings. On the steel side, you might have a same bay with steel framing and then lightweight concrete, for example, on top of the metal deck to form it. And on the right-hand side, you can see the steel framing, but with the mass timber, and then you still have a concrete topping on top of it, but a bit thinner for the acoustics. And this report, and if you want to get more details of it, it's all in the design guide, but it does a sample calculation of trying to compare them and study them. And as you're looking towards schemes, you can do something similar as you evaluate options and schemes in your designs. Likewise, you can do that with kind of a similar process that we're showing here. There are some really nice programs out there. There's lots of different ones. We're not endorsing any one of them. We've just shown 2 to show that there are differences in how you evaluate it and things like biogenic carbon and how you approach it. There's a whole methodology and discussion you could have in this, and we're just presenting kind of 2 paths to show some examples. And one is Athena and one is Tally. On the left-hand side is the Athena results, and you can see on the concrete side that, again, as we kind of discussed in the beginning, concrete has a lot of embodied carbon. There are things you can do for sure, but it's one of the most carbon-intensive materials we have. As you can see with the steel and lightweight concrete is even a little bit more carbon intensive because you generally have to get special aggregates and ship them over. It's not the normal aggregates you might have. So as you use normal weight concrete, you'll actually get a reduction. But you can see here on the right-hand side, or as you go further, you've got the steel framed with the CLT floors, including biogenic carbon and not. And the main takeaway there is, whether you count the biogenic carbon or not will change your equation. But in general, you're getting a reduction, especially compared to the concrete side. So that's there really are a lot of benefits on that carbon side. Again, if you can take any carbon out of that concrete and switch it with timber, generally there's generally a benefit there on a carbon footprint standpoint. Now, another guide you might use, or kind of a freebie tool I wanted to share with you, was this. It's called ECOM, Embodied Carbon Order of Magnitude Estimator. SE25, the Structural Engineering Institute, has set a goal for structural engineering firms to sign on to be trying to be net carbon zero by 2050. And as part of that, they provided this calculator where you can actually put in some estimates for any type of building, and it will give you an order of magnitude estimate of what the carbon intensity might be from a generic standpoint. So it's a good way to test different schemes and different options that you might be looking at, and at least be able to see a rough order of magnitude of what the carbon might be between those. The other benefit that is really not captured in that study, and is there's another knock-on effect of having exposed CLT as your structures. So from an embodied carbon standpoint, if you can get rid of your ceiling, that's additional carbon savings and embodied carbon if you can pull out that saving or that ceiling. Likewise, if you're a lighter building, and especially compared to what might be a full concrete structure, if you can get a lighter building, you're pulling out concrete from your foundations, and there's further benefits and reduced embodied carbon that you might be able to find there as well. So those are the other knock-on effects of being a lighter structure that you might capture from a carbon footprint standpoint. So the next section is about the structural design. And this was really geared towards structural engineers. And for the structural engineers listening on the call, there's other presentations that go into a little bit more depth. And there's full calculations. You can go crazy with lateral torsional buckling equations. We're not talking about that here. I'm going to walk through just a few of these items and what they look like to help give you a sense from an architectural student perspective of how things are put together, to help inform how you might draw a building section or what type of systems you might need to think about laterally and consider that as you're thinking through from a scheme standpoint. So the first thing is really about how does it connect it together? What does that look like? What does that detail look like? Well, it's pretty straightforward. You have a steel beam, and as you can see on that right-hand side, you will pre-drill holes on the upper portion of your flange, and as they drop in the CLT, you will essentially have specialized screws. They're called self-tapping screws that uses nominal drills like you'd buy at a sort of a box retail store, and you would screw in those screws from the other side very quickly. And typical spacing is somewhere around 18 inches on center, 12 to 18 inches on center, usually switching sides. And that's sort of that top picture, those sort of two ones, you can kind of see that spacing. There's another screw on the other side you can't see, but that's sort of a nominal attachment. And then the arrow that's behind it, I don't know if you can see from that image, but there's a whole lot more. Sometimes structurally we have larger loads that are actually in the floor plate that we have to transmit back into the structure, and we may have to increase the spacing sometimes for that. So that's really showing you kind of the different spacing you might see. As far as sizing the steel members for your structural classes that you may be taking, your high-level structural courses, the steel stays the same as probably any type of structural system that you've been looking at, and that's what makes it really nice. And that's one of the advantages of the system is the steel framing, by and large, how you approach it is the same as you would approach it with a steel frame building with metal deck and concrete. So you're not unlearning any of that. The only big difference is that generally we're not pre-cambering our beams. And what pre-cambering means is you bend your beams in construction so it actually settles and deals with some of the deflection as you pour on that concrete. Generally, we don't do that. And then likewise, if you heard that term composite that I said at the beginning, where you had those shear studs, and that actually has the steel and concrete act together, generally, we don't do that either with these floor plates. These steel beams are non-composite. So they are generally designed to be independent structurally of that timber. And so you'll generally be a little bit deeper than if you were a composite system because you no longer are relying on that the benefit of that concrete. There's also a full calculation of how to size your timber panel per the National Design Standard. That's the code. NDS is the term for the timber structural code to size your CLT panels. So there's a full calculation for sizing a 3-ply, 5-ply, 7-ply, how you might approach it. We're not going to go through it here other than to let you know that there's a full calc if you needed to see it in that design guide. On the lateral system side, what the lateral system structurally is your brace frames or moment frames. It's those elements in your building that are keeping your building from falling over effectively in a hurricane or an earthquake. And what you see in the middle there, you can see the ties. That's a braced frame. We are bracing the frames with tie elements. And that's one way that you could have a lateral system in a steel building. Another kind of common structural system is to use moment frames. And it's where you have generally a little bit heavier beams and columns, and they weld them together or bolt them together such that they move together. And the combined stiffness of the beams and columns together with kind of a rigid connection provides the stability of the frame. Think about your tabletop. Your tabletop generally is relying on that, your leg being into your tabletop to be firm enough to keep it from falling over. That's a good way to think about it. And the nice thing about this typology is if you've learned that or you've thought about that with another type of steel building, it is no different here. You've got the same considerations for seismic and wind, and you can use the same structural systems of brace frames or ties in a very similar way. And especially in seismic systems or seismic zones, and where you have to do more complex seismic systems for those in California, for example, having to deal with that, that's an advantage to the system. There's also a talk about a diaphragm. That really just means the forces that are inside of that tabletop. The tabletop of your table, the horizontal portion is actually keeping the legs together. It's keeping it together. That's kind of that's a diaphragm, a way to think about a diaphragm in a very high level standpoint. So there's lots of discussion there, and structurally it's a big deal to us, but from an architectural standpoint, generally not something that you need to know about in a very large detail. But if you look at the top here, the diaphragm, and it's really talking about how do you connect these panels together that have them act as a unit. Generally, the panels have a little piece of plywood. That's the light color. They're called spline elements that bridge over the two panels that screw them together. And likewise, we sometimes have metal strapping. Sometimes it's light gauge. Sometimes it's another element that also transmits forces and ties everything together. That's all part of the diaphragm system that you might see if you went out to site. Another consideration that you need to be a little bit careful of, again, from the acoustic conversation, is vibration, and especially if you're in a space like a medical building where you might have sensitive equipment, or if you have a really long span with a place where people are walking next to offices that want to be really still, and if they feel vibration and you're concentrating on work, you might be sensitive to it. Those are things you need to be careful about with these structures. We won't go into detail here other than that there's tools and ways to investigate that and actually measure the anticipated vibration you might get from footfall, for example. It's just a term that we use, footfall, of people walking their footsteps at different speeds, whether they're running or going slowly, and seeing how it impacts that structure. And finally, there's a section that really talks about details. So if you're interested about details and things about openings or moment connections and considerations, this would be a good section to go to. Again, the three things here that are probably most relevant is that camber. We generally don't camber our beams. You can have fit-up issues with these panels that are rigid, but it's really the penetrations and facade supports. And again, what we mean by that is the penetrations are the openings in your floor plate through those CLT panels. You need to be careful with those for your mechanical systems and think about those. You may have to frame around them. And 3-ply mass timber panels, they tend to have less strength redistributing load compared to the thicker plies. So sometimes when we evaluate the plies, if you remember, 3-ply is somewhere around 10 feet typically, 5-ply is 15 feet, 7-ply somewhere around 20 feet. Well, so that's about true, but also for openings and how you have to reinforce them, the size of openings that you can get in a 3-ply are much smaller before you have to add reinforcing compared to a 5-ply as well as a 7-ply. So if you have a lot of penetrations or you want a flexibility, sometimes you will choose to go to actually a larger ply, both for the longer spans and have a more open kind of span between your beams. You also may want to do that for flexibility for your penetrations and openings. And that's a consideration you look at holistically together a lot of times. And again, from a facade standpoint, you need to be careful with your facades. A lot of times the mass timber panels can't really take a large concentrated load on their weak axis, especially for something like CMU or masonry. If you're to have brick on your facade, generally you're going to need to have another structural steel member or other way of reinforcing that panel to pick up those loads. And sort of the same shelf angle details you might have looked at or thinking or ways you might have supported your facade with a steel building will still apply here. On the constructability side, this was really geared towards a high level chapter towards contractors. Really the main things we talk about are procurement, thinking about the erection process, tolerances between different materials, especially concrete and CLT. You can have some issues with fit up and tolerances, and how to think about those. Likewise, how to protect that timber during construction and if there's a fire risk. You know, one thing to note in this table is as you get CLT panels or other mass timber products, and you want to optimize your structure for that framing, you might actually look at engaging a mass timber supplier or specialist in what's called a design assist process during your design phase. So there's different ways of addressing it. Sometimes you do, sometimes you don't. But really, this chapter was meant to talk about those issues holistically and other resources, again, geared towards contractors for these considerations. So believe it or not, we've come to the end of those sections, and that was a lot of information. You know, I think this next section is to take a breath now and say, okay, oof, that was a lot. Help me put that back together. What does that look like in an actual building and a case study? And that's what we're planning to do here, is to touch base on those issues with the Houston Endowment headquarters. That's the building that you see at the top of the hill here in a rendering. It's a project by Kevin Daly Architects, as well as with Productura. It was really a fantastic team, all listed here. But it's around a 40,000 square foot commercial building in off of a sort of a greenway in downtown Houston and near downtown Houston, and really meant to serve as the foundation headquarters. And as you can see here, this is a rendering from the lobby with the main lobby stair. You can see the steel framing here and then the CLT spanning behind it. It is just finished completion and is a steel and hybrid mass timber structure for a lot of the advantages that we talked about way back at the start of this presentation. What does it look like from the outside? Kind of zooming in, you can see the mass of the buildings of kind of the two levels of the office space over a partial basement parking garage, and then connecting all of it together is a really elegant canopy that's serving both to shade but also support the photovoltaic panels. And Kevin Daly Architects were looking at this project, and Productura. Sustainability was a big key driver. There was a big international competition, and really net zero was always the goal and striving of this project from an operational standpoint. And a big reason of having that canopy is actually to provide the PVs in order to have try to get net zero by getting energy from the sun. Also, that canopy is trying to keep the heat gain of our really hot Texas heat. That air conditioning load is a big driver of that operational carbon, and that shading takes a lot of that thermal energy. Just like if you pull your blinds, if the sun is shining through your window and you pull your blinds are really helping stop a lot of that thermal heat come directly. And the way to think about that canopy and that shading benefit is if you took those blinds and then you went even further and didn't even let it come through your glass, you get an added benefit of reducing those loads. So really the building was really conceived around that sustainability and that experience and openness and flexibility. And during schematic design, it was actually in a fully concrete structure. And the reason it was concrete was trying to use radiant tubes that were cast into the concrete to use radiant heating. And again, that goes back to the operational carbon side. There's a benefit to radiant cooling and having even lower energy demands. And there's a plus there. But the negative was, as we went through schematic design, it was a heavier structure. And we actually had very poor soils at this site. This site used to be an old YMCA building. There was some fill on certain portions, and it has expansive clays, and we had a very heavy foundation. Likewise, with some of these spans and openness that you can see, the concrete required shoring and formwork across the entire building almost for all three levels. So it required a pretty heavy crane. It also required a very long construction schedule to shore everything and form it up. And all of that led to essentially the structure being out of budget by about a factor of 2 at the end of schematic design. And we had essentially a crisis at that point. And this is an amazing project. How do we rescue it? What can we do? What are the options out there? And we really had a narrative as a team of looking at the sustainability and taking that from an operational standpoint and thinking about it to solve this problem. Steel framing and hybrid really was a natural, it came up very quickly, and we schemed it up really in like 3 days and presented it. And it was driven by the aesthetics. It was still really beautiful. It has similar sort of exposed structure. It also was much quicker to erect. It's all steel framing, everything. The steel's effectively prefabricated in shop, brought up and bolted, and then the panels are brought in. So it's much faster. Likewise, it's lighter. It's significantly lighter than that concrete structure. And so we pulled out a lot of the costs and a lot of the issues in the foundation out. So we ended up with a structure at the end of the day that was lighter by about half. We pulled out about half of that carbon. Also, all of that concrete was heavily carbon intensive. And so we were able to pull all that carbon out. And likewise, it was faster to install, and and it was better from those other aspects aesthetically. So it was a great solution. Everyone was brought on board, sort of brought the project back in budget, and we sort of kept moving forward. Again, as part of that, just to that e-com tool, we actually did a quick study at the time just to see it and help inform it. These were just based off of scheme numbers at the time, but you can kind of see the reduction of carbon by about half. The floor plate and how it's built up is on that second level is using a raised access floor. And that was selected for a number of reasons. A big part of it was flexibility from an MEP standpoint. They could put in the MEP, they could hide it, so you're not seeing it, but also for adaptability in the future, you can lift up those floor tiles and access it. And if you were to change an office or change a space or change the routing, there's a lot of flexibility to do that at that level. It also kind of hid the acoustic sandwich and everything else that was below that. Structurally, we have moment frames. If you remember on the structural side, what lateral system should you use? Well, in this one, we use moment frames where we have rigid beams and columns acting together that are spread across the building. And we did that to distribute the load because we needed to spread out our forces because of our foundation. So we wanted to make our loads as uniform as possible, including our lateral loads. And we see hurricanes down here in Houston. So there's a lot of load, especially with that canopy blowing into this building that we had to deal with. Also, it allowed flexibility. Braces are great. They're very efficient. They're cost effective. A lot of times from a steel standpoint, but you can't walk through them. And this was a very flexible space. I wanted to be an open space, and this allowed us to get rid of braces within these office spaces. What does it look like on plan? This is the second level. You can see there's some large kind of atrium openings on the sort of the right-hand side. You can see the main lobby stair that faces south into the park. There's a little bridge there. That's the main opening of the building. And on the left-hand side, there's another big kind of signature stair and atrium opening connecting the two levels as well. And really a couple of things to draw your attention to from a detail standpoint to help you visualize it. Again, on the left-hand side, what you're showing there is a big cantilever. Again, this is one of the advantages of steel compared to, for example, a full mass timber building. You can certainly use glulam beams and have cantilevers, but they tend to be deeper and can sometimes be more expensive. Steel deals with cantilevers. It's a very high performance material. You can weld double cantilevers together. It's a good material to deal with these type of conditions. And we utilize this on this building to have some cantilevers for key conference rooms and meetings on the outside faces. Likewise, for the opening of the atriums, we're able to have simple steel to go around to connect to then clip on all the handrails and other architectural components. Vibration was a big issue. Where we had our columns and the offices, we had our main walkways. And so people walking across, it's kind of like a diving board as people would go across those main corridors. There's people kind of behind them that would be working away at a desk. And we did have to consider how it might, how that vibration would behave and upsize some beams in order to deal with that. And structurally, the steel provided a really clean way to integrate a steel canopy that was always going to be steel back with the structure. We have really large loads in that canopy. All those louvers act like a little sail and pick up a huge amount of load that has to go back into the building. And the steel provided a clean way to deal with those forces. Steel connections can deal with high level of forces in a very elegant and clean way compared to other materials. And we took advantage of that in this project too. And again, just what does it look like from the top side? You can see those splines that we talked about, those pieces of plywood connecting the individual panels together that are then nailed or screwed on both sides. And you can see the metal strapping that are also serving as part of the lateral system to have the whole tabletop here of the CLT act as a cohesive unit. And finally, it was a very tight site. This was it. It was the whole building. The crane here was the only crane on site. And the CLT panels would essentially be backed up into the truck and dropped and installed over a course of a day for an entire level. So it was a great way to deal with this very constrained site. There was an apartment complex just across the street that they didn't want to disturb and they had to deal with. And so that was another advantage of the system. And again, some pictures just to show it during construction. There actually was a concrete and metal deck as part of this project. The bottom floor was still concrete and metal deck because of the parking garage below, but you can kind of see the steel and hybrid floors where it's utilized for the office component here. And you can see the atriums that we're able to get kind of going through where the stair is. And again, another view of the lobby, and able to use steel and the steel framing to have some fun lobby stairs. And just looking before they put in the raised access floor, again, so why would you consider a raised access floor? Well, here's a great image of all these utilities in MEP. You can absolutely route them and coordinate them, but if you don't have them here, they got to be in your ceiling, and that's covering your steel and your CLT potentially. So that's one of the drivers or benefits. So there's certainly a cost that you got to weigh, but that's one of the advantages there of that raised access floor. And again, another image. You can see the penetrations with the sprinkler pipes to keep them high, but generally trying to take away all the other utilities to expose that CLT spanning between those beams. And again, this was opened just recently, and you can actually go visit it and walk around it in the site with the canopy. But it's a beautiful building. Very successful, and was a great experience, and hopefully it was helpful to show how steel framing in a mass timber building was applied in a real project, how all those considerations on acoustics and fire and everything was put together in a real project there, and to see the advantages that I was able to utilize to get the project kind of back on schedule. And with that, that's really my last slide. Thank you for going through this guide with me. I hope it was useful to you, and it's really been my pleasure to present this.
Thanks so much, John. We really appreciate your sharing your expertise, and this was fascinating, even for a non-architecture student like me. I'd like to thank everybody for participating in the webinar. And again, our gratitude to AISC for arranging this and for their partnership. And be sure to review Gene's introductory slides about how you can go about getting HSW credit for this webinar. Thanks so much, and I hope that you have a good rest of your day.